Today we're going to discuss how to write balanced chemical equations. Chemical equations are just a short form that scientists use to communicate what's happening in a reaction. We write them as symbols so that we get a single line of text instead of writing a paragraph worth of information. A single balanced chemical equation can tell you these four things: what elements are involved in a chemical reaction, how those elements get rearranged. Those are the types of reactions we talked about previously, the single displacement, double, synthesis, decomp, combustion patterns. Number 3, what amounts you need to mix your chemicals in. And number 4, they let you know how much of a product will be made. Here's an example to have a look at. If we take CuS plus NaO, what type of reaction does this look like? Remember to identify elements. Look for capital letters. Here I have one element plus another stuck together in a compound. This is copper sulfide. Plus two more elements because I have two more capital letters stuck together in a compound. This compound is sodium oxide. So if you have two elements plus two elements, this looks like a double displacement pattern. To predict what gets made, if you have a look, the first is going to go with the last. So we're going to make some CuO. Then the third is going to go with the second, and we're going to make some NaS. This is that double displacement pattern we discussed. So to answer our questions down below, what elements are involved in this reaction? There's copper, sulfur, sodium, and oxygen. How did they get rearranged? They got rearranged in that double displacement pattern. First goes with last and third goes with second. What ratio do you need to mix them in? To get that, you look if there's any numbers in front of the chemical formulas. Because there's no number here, we assume there's a 1. So I need 1 CuS mixed with 1 NaO, and that's going to give me 1 CuO and 1 NaS. And that's also how you figure out how much chemicals gets made. You look at, well, how many formulas do you have here? I'm going to have 2 chemicals made, 1 of each, because there's no number out in front. Here's another example. When you burn steel wool, what type of reaction does this look like? Here you have one element, because there's only one capital letter, plus another element. The only thing I can do if I've got two elements reacting together is to squish them together and make one product. That's the definition of a synthesis reaction. So my iron and my oxygen are going to get put together. So what elements are involved? Iron and oxygen. How do they get rearranged? We do the synthesis pattern. If I take one iron and one oxygen, then I will get one iron oxide. When performing chemical reactions, scientists have noticed something really interesting. If you perform a chemical reaction on a scale and track how much your container weighs, there is no difference from the reactants to the products. And this is known as the law of conservation of mass. During a chemical reaction, the total mass of the chemicals that you have never changes. That means that the atoms that you have cannot be created or destroyed when you're doing a chemical reaction. When we're writing equations, we need to make sure that we always start and finish with the same number of atoms so that we're following the law of conservation of mass. The first skill you need is to learn how to count atoms in a chemical formula. Remember that elements can be identified whenever you have a capital letter. All element formulas have a capital letter, with some elements having a lowercase letter attached to them. Also, chemical formulas may have what are called subscript numbers, numbers that are written small and low after the chemical formula. That tells you how many each atom of that particular element there are in the compound. These subscript numbers only belong to the element symbol that's written in front, not the element that's written behind them. If you only have one atom of a particular element, we don't typically write a subscript number. If there's no number there, there's actually a little invisible 1 there. So let's count the number of atoms in some chemical formulas. Here we have magnesium chloride, or MgCl2. Notice I have 2 elements here. The Mg, that's the 1. I know that it's 1 element because here I have another capital letter, which stops the first element. And then here I have another element, Cl. You notice that there's no number after the Mg. That means there's a little invisible 1 there, so we have 1 magnesium. And this little subscript 2, it's written small and down. That is attached to the chlorine, only the element in front. So here I have 2 chlorines in that compound. Try out K3N and Al2P3. Pause the video here and figure out how many of each element are in that compound. Here are the answers. In K3N, this 3 is only attached or belongs to the element in front, that K, which is potassium. So here we have 3 potassiums, and there's no number after the capital N, so that means we have 1 nitrogen atom. For Al2P3, this 2 belongs to the Al, so we've got 2 aluminums, and that 3 belongs to the P, we've got 3 phosphorus atoms. Because the law of conservation of mass, we need to make sure that the number of atoms on the left side of our equation equal the number of atoms on the right side of an equation when we're discussing a reaction. And so this is called balancing the equation. What you do is you pick an element and count how many do you have on each side of the reaction arrow. If they're the same, great. If they're not the same, you add what's called a coefficient, which is a big number in front of that element symbol that multiplies your formula. And you can use trial and error or guess and check to figure out what coefficient you need. You need to make sure that there's the same number of atoms for that particular element on both sides of the arrow. Then you pick another element and do the same thing until you've made sure that you've balanced every single element in your equation. When you do this, you may need to go back and recheck to see if balancing one element messed up another one that you've already checked. It's really important to know that you can only add coefficients, these big numbers out in front. You cannot change the little formula subscripts in order to make this work. If you change the little subscripts, that'll change what kind of chemical you're using, which will then give you a different kind of reaction, not the one we're looking at. An everyday example of writing a balanced chemical equation is like writing a recipe to make a sandwich. There's 2 ingredients to make a sandwich. If you take some bread and some meat, then you can make a sandwich. But what we're going to do, this is like a word equation. Using the names of the substances, we're going to change those into some symbols. So we'll take bread as a capital B, meat as a capital M, and in order to make a good sandwich, you need 2 slices of bread and you need at least 3 pieces of meat. Notice that this equation that I've written here is not balanced. On the left side, I only have 1 bread, but on the right side, I have 2. To fix that, what we do is we add a big number out in front that multiplies the element or the item that we're using. So now I have 2 breads on each side. To balance my meats, I have 1 meat on the left, I have 3 on the right. So to make them the same number, I stick a coefficient of 3 on the left side of the equation. Now you notice I don't have any meat or any bread coming out of nowhere or disappearing on me. I have the same number of items on the left side of the equation as I do on the right side of the equation. Now, scientists wouldn't write an equation like this. What we would do is we'd actually simplify how we write the symbols for our sandwich. You notice I have 2 breads, so I would just write the B once and stick a subscript number of 2 behind it. And I would do the same thing for my meats. If I've got 3 pieces of meat, I would show it by a capital M with a subscript number 3. But you notice the balancing process would be the same. On the left, I got 1B. On the right, I got 2. I need to put a coefficient in 2 on the left side. On the left side, I've got 1 meat. On the right side, I have 3. So I would need a coefficient of 3 in front of that meat. Now I have a balanced chemical equation following the law of conservation of mass. Let's look at a chemical reaction and follow the same process. Step number 1, pick an element and start counting. On the left side, you notice I have 2 hydrogens. On the right side, I've got 2. So that's okay, it's balanced. I don't need to add any numbers. Now let's check the oxygens. On the left side, I have 2 O's. On the right side, there's no number there. And that 2 only is attached to the element in front. Because there's no number after the O, there's a little invisible 1 there. So I have 1 O on that side. Because I don't have the same number on each side, I got 2 on the left and 1 on the right, I have to fix it by putting a coefficient out in front. Remember, you cannot just add in a little 2 there. The reason why is because H2O is the chemical formula for water. H2O2 is the chemical formula for hydrogen peroxide. You might have some in your bathroom cupboard. Water and hydrogen peroxide are 2 very different products. If you change the subscript numbers in order to balance, then you're actually not describing the chemical reaction that we want. So let's get rid of that little 2. In order to make 2 O's on the right-hand side, I can only put big numbers out in front, coefficients. Now this coefficient of 2 is going to multiply all my atoms, all my little subscript numbers. So here I've got 2 O's on the left. This gives me 2 times 1, or 2 O's on the right. So now my O's are balanced. But you notice now I've messed up my H's, because now I have 2 times 2, that's 4 H's on the right. I need to put another 2 on the left in front of my hydrogens to get 4 H's. 2 times 2 gives me 4 H's. Here are some tips, tricks, and strategies you can use. You will hardly ever use a number higher than 6 as a coefficient. Sometimes you have to, but they're rare. So as long as you are comfortable with up to your 6 times tables, you can pretty well do them just in your head. But if you're a little dicey with that, bust out a calculator to help you. That's okay. When you're picking elements, I always balance my oxygens and my hydrogens last. If you balance the other elements first, it often makes it easier to balance your O's and H's. Tip number 3. If you ever have 2 atoms on one side and 3 on the other, you're looking for the lowest common multiple. Turn them both into 6. That's a really common strategy you have to use. And tip number 4, you can use halves as your coefficients, but you can't leave them there in your final answer. To get rid of them, you have to multiply everything in your equation by 2, because a balanced chemical equation always has its coefficients as whole numbers. And also, they always have to be in lowest terms. Let's have a look at this example here. What elements are involved in this reaction? Well, we have a calcium, a chlorine, and an aluminum. How do they get rearranged? Do you notice how the aluminum is stealing calcium's partner and kicking the calcium out on its own? Hey, that's our classic single displacement pattern. To figure out what ratio do you need to mix those chemicals in and how much product will be made, you need to make sure your equation is balanced. So let's do that. Here on the left, I've got 1 Ca. On the right, I've got 1 Ca. That's the same number, so that's fine. But you notice for my chlorines, I have 2 Cls on the left and I have 3 on the right. I need to add some coefficients to make these the same number. One of the tips we just talked about is if you have 2 on one side and 3 on the other, turn them both into 6. So if I put a 3 in front of my CaCl2, this will give me 3 times 2, or 6 chlorines. If I put a 2 in front of my AlCl3, this will give me 2 times 3, or 6 chlorines. Now my chlorines are balanced. But you notice that messed up my Cas. Here I have 3 Cas on the left, so I need to put a 3 there to give me 3 Cas on the right. In terms of aluminums, I have 1 Al on the left, I have 2 Als on the right, so I need to put a coefficient of 2 on the left-hand side. So what ratio do I need to mix these chemicals in? I need 3 calcium chlorides for every 2 aluminums I mix together. And when my reaction is finished, I'm going to get 2 aluminum chlorides and 3 calcium atoms out. Let's try one more example. What elements are involved in this reaction? Well, C, that's the symbol for carbon, this capital H, hydrogen, and this O, oxygen. How do the elements get rearranged? Notice I have a chemical with C's and H's in it. I'm adding it to oxygen, and I only get out CO2 and water. This is a complete combustion pattern. Let's balance this equation. Notice I have 2 carbons on the left, but I only have 1 on the right. I need to put a big coefficient of 2 in front of my CO2 to make sure that I have the same number of carbons on both sides of the arrow. Let's now do the hydrogens. Notice I have 6 hydrogens on the left, but I only have 2 hydrogens on the right. In order to fix that, I need a big coefficient of 3 out in front. Now I have 3 times 2, that's 6 H's and 6 H's. Now let's look at the oxygens. On the left side, I only have 2. And on the right side, you have to be careful. You need to add all the oxygens on that total right side together. So here I've got 2 times 2, that's 4 C's in my CO2, plus 3 times 1, I have 3 more oxygens from my waters. So I got 7 O's total on the right-hand side. In order to balance this, I need to figure out, well, what number times 2 will give me 7? This is a more difficult one because it's not a whole number. But if I throw in a 3.5, 3.5 times 2 will give me 7 O's on the left, and now I have my 7 O's on the right. So my equation is balanced, But I can't leave this as my final answer. Balanced chemical equations always have whole numbers. So to fix this, I'm going to take my equation and I'm going to multiply everything by 2. Because if I times a half by 2, I'll clear that fraction out of there and I'll just be left with whole numbers. So instead of having one C2H6, I'm going to have 2 of them. And 3.5 times 2, that gives me 7 O2s. 2 times 2, that's going to give me 4 CO2s. And 3 times 2, that's going to give me 6 waters. Now my equation is still balanced, and I have all whole numbers as coefficients. Let's double check to make sure it's still balanced. On the left side, I've got 2 times 2, that's 4 carbons. This is for 4 carbons, 4 times 1. For my hydrogens, I have 2 times 6, that's 12 H's. On the right side, I have 6 times 2, that's 12 H's over here. Then on the left side, I have 7 times 2, that's 14 O's. And on the right side, I have to count all the O's together on the side. I've got 4 times 2, that gives me 8 O's from my CO2, plus 6 times 1, that's 6 more O's I need to add together. That gives me my 14 oxygens, both on the left side and the right side. Now that I have this equation balanced, I can discuss what ratio I need to mix my chemicals in. In order to have this complete combustion reaction happens, I need 2 of these fuel molecules to react with 7 oxygen molecules. And that's going to make me 4 carbon dioxides and 6 molecules of water. Now try out the balancing equations and identifying reaction type worksheet.